All right, today we're going to take a look at section 1.1, which is titled Real Numbers. Some of the things in this section are directly related to my title. Other things are sort of just building blocks that we're going to need as we continue working our way on, so a little bit of a review section from some things that you've seen before. One of the things that I kind of want you to know is that there's going to be most of what we do that you've seen before. It just is. A lot of this content overlaps with things that you've already done. But maybe you didn't have a very firm grasp of it before. Maybe you didn't have the best math teacher. Maybe it wasn't your top priority and you just absolutely do not remember how to do certain things. So for some of you, you're going to be like, I already know all this. And maybe you do know a lot of it, but maybe you need some brushing up on some things. And for others of you, you're going to be like, I don't remember ever learning this, and that's totally fine as well, okay? So we're going to get started. The first thing we're going to do is we're going to take a look at kind of a visual display of the real number system. So real numbers can sort of be split into two separate categories. The category over here on the left with all the boxes are our rational numbers. And we'll come back to them in a minute. That's a little bit thick of a pen. Let me make that a little bit thinner. The other side are our irrational numbers. Irrational numbers has one box, so I'm going to talk about it first. Irrational numbers are the kind of numbers that you tend not to learn early on. So the first irrational number that you probably ever encountered was in middle school, and it was the number pi. Okay? You might in your mind be thinking, well, pi is equal to 3.14. It's not equal to 3.14. It's approximately 3.14. But it continues on with no repeating pattern forever. Another number that you would have countered, if you did so, probably in high school, was the number e. The number e is approximately 2.718. Again, not equal to, but approximately. You encounter it when you do things in like Algebra 2 with interest, compounded continuously, or continuously compounded models of like bacteria growing or something like that. That's where you would have seen that, if you've seen that one. Another one that you would have seen most likely in high school is something like the square root of 2. So square roots where you can't simplify them nicely, right? So square root of 4, no problem, we can simplify that. But square root of 2, not so much. It's about 1.4. Again, about. It doesn't have any way to stop the decimal expansion or to terminate it because it then starts to repeat. So those are irrational numbers. We're not going to be working with those for quite some time, at least not directly. We'll see them just a tiny bit today, but in a little bit different fashion. The rational numbers is where you actually start. In fact, we're going to start in that tiny little box in the middle. The tiny little box in the middle is the numbers that you first start to count with when you're little bitty, and these are your natural numbers. So when you first learn to start to count, whatever my 6-year-old, when I say, hey, count to 100, what number does she start to count with? 1, right? She goes 1, 2, 3, and she keeps going until she can't go any further or gets confused and skips a bunch of numbers or something like that, right? Those are natural numbers. These also have another name that you will sometimes hear. They're sometimes called the counting numbers because they're the numbers you first learned to count with. All right, but very quickly, even my daughter will find that when she first learns to subtract and she says, I have 3 apples and I give 3 apples away, how many apples do I have left? I don't have a number that represents this if these are the only numbers I have. I also need the number 0. So if I expand my universe just a little bit, I have what are called whole numbers. My whole numbers, I'm going to leave the word numbers off of all these so that they're consistent. My whole numbers include all the natural numbers and 0. So you don't get a whole heck of a lot more. You just get one additional number, but it's a pretty important number to have. We need the number 0. So what you see in this diagram is sort of a nesting dolls. Have you guys ever seen the dolls at Christmas time that go one inside the other, right? They're usually Santas, but they're snowmen and other things too. They're nesting dolls. Well, this is a nesting diagram. The natural numbers are contained inside the whole numbers because natural numbers are whole numbers. And here in a minute, I'm going to expand the universe just a little bit bigger, and it's going to include the integers more generally. And integers occur somewhere around 5th or 6th grade for kids usually. And that's when we sort of have the idea of, well, what happens if I do 5 minus 7? I don't have a number that represents that, right? What does that actually mean? Well, it means I have $5 and that toy at Walmart costs $7 and somehow I need to acquire 2 more dollars. It's a negative number. So integers include, we're going to put the ... at the beginning, all the whole numbers already, and then they also include the opposites, the additive inverses, right? The negative parts of them. So again, natural numbers are whole numbers, and natural numbers and whole numbers are both integers. And they're both inside this bigger rectangle already that's called rational numbers. What kinds of numbers have I not included so far on my diagram anywhere? Fractions and decimals, right? At least certain kinds of fractions and certain kinds of decimals. So some examples, I can't do this sort of ... kind of a picture of them, but some examples would include fractions like, 1/2, right? It's a fraction. It would include decimals like 4.1. So how in the world do these numbers that have these sort of decimals differ from the irrational ones? Well, they differ from them because they stop or they repeat. So another kind of number over here would be the number like this, 0.3 repeating. Right? Repeating numbers are rational numbers as well. So why are they called rational numbers? Well, they're called rational numbers because they can be written in a ratio. For example, this 0.3 repeating as a fraction is 1/3. It's a ratio of integers, hence rational. You can't do that with pi. There's an approximation for pi, 22/7, but it's not exact. It does not have a ratio designation that we can make with integers. Okay, so like there are fractions, we can do fractions over here inside of irrational as well, but they're fractions that won't have that form, right? They'll have something of this nature in it, like if you had square root of 2/2, or if you had pi/6, depending on what kind of math classes, you may have seen numbers like that before. Those are also irrational. They're fractions, but they're fractions that include irrational components, not just whole number components or integer components. So some of the questions you have, we're going to be dealing with categorizing or thinking about how numbers are related to our number system. Something else in this section that we're going to take a look at is graphing. And we're talking about two-dimensional graphing, not an XY ordered pair kind of graphing, but on a number line. Okay? So I had this in here from yesterday, so I left it here because we'll use it again. But to start with the first one, when we think about a number line, what we want to remember is that a number line is how we read in English, which means that we read from left to right. So we order our numbers from smallest to largest from left to right as well. So on our number line, if we're trying to graph, like on this one, the number 2.3, we need the number 2. And we need somewhere over here the number 3, right? Because 2.3 is going to be in between them. So we can actually partition it off. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 would be the number 3. So are there other numbers on the number line? Well, yeah, there's lots of numbers, but don't go putting more than you really need on there. Just give a reference point. It's between 2 and 3. In particular, on my diagram, it's right there. So a dot, a solid kind of a dot, and then labeled is a good way to represent that. All right, taking a look at the next one, I've kind of narrowed the focus a little bit further. It's wanting to know that red dot, where is it? And now I'm not between 2 and 3, I'm in between 2.2 and 2.3. So what's actually happened is instead of having 1 decimal point for that location, I'm going to need 2 decimal points. So if you think about each of my hash marks now, this one up here would be 2.21, right? And the next one would be 2.22. What in the world is the red one that's noted right here? you tell? It is. It's 2.26. If your eyes don't go cross trying to count my little hash marks anyway, right? 2.26. Decimals are really nice because we have a reference point that we use for decimals all the time in our money system. So one of the ways you could think about this particular diagram is that this is much like having $2.20, right? And this is like having $2.30. So the number that I'm dealing with between them is really just $2.26. That's the idea. It doesn't, oh man, it's off the screen. That's super weird. I'm so sorry. Let me move those up at least. I'm not sure I've ever seen that happen before. Okay. Well, you can at least see it now. They've got some weird marks going on, but oh, for pity's sake. All right, that's better. So 2 decimal places are really nice for having sort of a real-life application that we use all the time. If you expand to 3 decimal places or 4 decimal places, we don't have quite that same visualization, but the process works the same. Any questions on either of those with graphing? Okay. If we were working with negative numbers, we would just go the other direction, right? We'd hit 0 and we would count kind of backwards. That's what it looks like. We would go -1 and then -2 and then -3 and so on. And you could definitely encounter something with negative numbers in terms of the graphing questions asked. All right, inequalities. Inequalities are very useful for us, giving us a way of ordering values together. There are actually 5 inequalities, although we don't see the not equal to one used all that frequently. It is still an inequality. And each of these have meaning or names for them. So the first symbol, what is that symbol representing? Do you remember? Close. It's the less than one, actually. So one of the mnemonic devices that you can remember for the less than symbol is that it looks kind of like an L on its side. That's one of them. The second one is, if we go down, is greater than. And the one underneath greater than, of course, is, yeah, it's not equal to because of the slash through it, right? Okay, the ones next to them, sort of in my second column, have an extra line underneath them. What does that extra line mean? Yeah, it's an or equal to. So this one is actually less than or equal to. Now, it can't be both. It's one or the other. But it's kind of a more flexible symbol than the previous one because it gives you 2 options. It's the option of less than or it's the option of equal to. And then the last one, of course, same idea, is greater than or equal to. All right, so taking a look at the example here, we have 4 symbols options given to us, and it wants us to fill in the blank with one of those 4. So sometimes your questions will give you more options, and sometimes they'll give you fewer options. There are actually 2 different answers that would be correct to put in that blank. So can somebody give me one thing that you could put in the blank that would be correct? Yes, greater than. Greater than would be correct in that blank. What's another option that we could put in that blank? Okay, not equal to is not one of my choices on this particular, and I only have these 4. It is not equal to, but I don't have that as a choice. What else could I use? Yeah, the greater than or equal to, the one with the line underneath. And either of those would be correct. So be careful on your homework to make sure. I'm glad that you guys actually thought about the not equal to because it's actually true. But make sure and use one of these symbols it asks you to use in the blank. Sometimes, it could actually restrict it so you didn't even have these options, right? You only had those first two, and in which case you're sort of narrowly defined to only pick one or the other. You don't have a choice. But if you have more than one choice, you have more than one answer, that's okay. And your answer could be different than mine and both be correct. I mentioned square roots earlier. I mentioned specifically the square root of 2. Here, I'd actually like to talk about what happens when you have nice square roots instead. So when you have square roots, what it's actually asking you to do is to find one of two equal factors of a number. Okay? So for nice square roots, that's very clean and very straightforward, kind of. So principal square roots, you may or may not have heard that phrase before, are the ones that we work with the most often. At least at this point in the semester we will. This is the non-negative square root of a number. For example, if I were to ask you, what is the square root of 64? And your first gut reaction, what would you tell me? You'd probably tell me 8. And if you did, that would be the answer for what the principal square root is. Okay? Now come up here for a moment, and let's actually say that the question just said, find the square root of 64. Well, there's actually two of them. There's 8 and there's negative 8. Because what is negative 8 times negative 8? 64. Well, that fits the description of a square root. It's a number times itself that equals 64. So how do we know when the answer is just 8 and when the answer is 8 and negative 8? Well, the way that we know is by the symbols. If a problem is given to you with the square root symbol on it, it's not asking you for the square root of 64. It's actually asking you, what is the principal square root of 64? That's what it's asking you. What is the principal square root of 64? And the answer is simply 8, the positive part. So sometimes you could remember this maybe as anytime it gives me a radical already in the problem, it just wants the positive value. It doesn't want all the values. It just wants the positive value only. So when would we want both of them? Well, we'll encounter that later this semester. Specifically, we'll have both of them when we're solving quadratic equations. For example, you might remember problems like this from high school when you said, what is x squared equal 64? What number solve that equation? And somebody said, hey, you take a square root, but whenever you put a square root on, you have to remember to put plus or minus. Y'all remember that? That's when the negative square root part comes out, okay? In the middle of solving equations. So we're not dealing with that right now. We're not worrying about the negative part of this because we are going to be given problems, at least in this section, that already look like this. They've got square root already on there, so they're asking you for the principal square root. Sound good? So jot yourself a note, something right now that just says, if there's a square root, I'm not asked to give the negative. I only need the positive part. All right. Did you know that in real life, approximations are often good enough? Have you encountered that? I don't really need to know exactly how tall you are. I just need to know approximately, right? Often, approximations are good enough. So a perfect square, like we encountered with the 64 just a moment ago, is a number with a square root that's a rational number. Right? I can take the square root of 64 and I get something beautiful, 8. But 65, not so beautiful. If I take the square root of 65, I don't get a nice number. I get something with awkward, weird decimal expansions. Right? It's not a perfect square. Can you give me an example besides 64 that is a perfect square? 36. Absolutely. Can somebody give me another one? 4. All right, let's add a couple more over here on my non-examples. What's another example of something that's not so pretty? Huh? 9? 9 is pretty. Square root of 9 is wonderful.
17.
17 would work, yeah? 27, not so nice. Maybe one more. 21. All right. So some things are fantastic. They give you really whole numbers. They're really nice. And there's actually ability they could give you some decimals, and those would be nice too. But they're like closed-ended decimals, right? That they end very nicely. So anything that has a rational number when you take the square root, remember rational number means a decimal that ends. Like if you did it in your calculator, it would actually give you a decimal that ends. That's a perfect square root. And anytime it doesn't happen, then it's not a perfect square root. All right? Or a perfect square, I should say. So what we would like to do is be able to use that idea to approximate something. So did you know that back in the day, this is before my time, so like way back in the day, way, way, way back, but your calculator couldn't do square roots. There was like derivations of how to find like the decimal expansion for like the square root of 20, and like people would do that. If you have ever had the opportunity to watch Hidden Figures, highly recommend the movie. It's fantastic. It's about the NASA space program and the mathematicians, really, and it was black mathematicians, black women, who were the mathematician, the one that's primary in the movie, behind all of the derivations of the trig functions that your calculators do like that now. Absolutely fantastic movie. Well, that's the kind of thing that people did before your calculator had the little square root button that you pushed and it gave you some numbers out of it. But the reality is we can actually start that process fairly easily. So what I'd like for you to do is to write down the number 20, and I'd like for you to pick two numbers, one on each side of those, that are perfect square roots that are close to 20. So do it for me just a second, and then I'll ask you what you have, and we'll make sure we're all on the same page. So a number slightly bigger than 20, a number slightly smaller than 20 that are perfect squares, because 20 isn't. Okay, what's the number you wrote down smaller than 20? 16. Yep, that is the one that is most closely connected or closest to the number 20 that's perfect. What about bigger than 20? 25. Okay, so think with me now. What is the square root of 16? 4. And what is the square root of 25? 5. So what do you suppose you can tell me about the square root of 20? Is between 4 and 5. Absolutely. That's sort of one of those things that you should be aware of when you hit the square root button in your calculator. So when you hit square root 20 and it pops back out an answer, you should have some expectation of whether or not it makes sense. Because did you know that sometimes when you use your calculator, you hit the buttons and you didn't mean to hit and you end up with a typo? Has it ever happened to anybody but me? I mean, it happens. So if it spits back out an answer for you that says, 6.2, there should be a red flag that goes off in your head that said, oh, I must have hit a wrong button. I must have. Some calculators you can see what you hit before, and some you can't, especially if you're using like the scientific one in your calculator, in your phone. You can't always see what you just put in the slide before or whatever, the keystroke before. So the square root of 20 is actually between 4 and 5. So when you're answering the questions that look sort of like this on your homework, I expect you to find for me the two numbers on either side and show me why it has to be between. Well, it has to be between 4 and 5 because 20 is between 16 and 25, right? It has to follow because this is an inequality statement. So the answer to the question then is square root of 20 is between 4 and 5. If you only give me that as your answer, you're going to miss part of the question because you haven't justified why it's true. Because I don't know what you did. I don't know if you actually just grabbed your calculator and put in square root of 20 and you got out an answer that was 4.6 and you're like, well, it's between 4 and 5. Well, then you're not thinking through the mathematics of the reason it had to work that way. Does that make sense? So that's what I'm looking for. I'm looking for you to justify why. Why is it between 4 and 5? Well, there's a very simple reason. And it's not hard to explain, but I want you to show me that you know how to do that. All right, any questions on that? Okay, so if you're working in this book, what you will see now is that you're at the end of the lesson, right? And it tells you on the bottom that your homework is number 1, real numbers. So what do you need to do for me before Thursday? Because we're about to end. Well, before Thursday, If you don't have an iPhone, you need to find a PDF scanner, another app or something that you want to use, okay? If you do have an iPhone, then you already have it. You can play with it. You can see how it works. That's great. You need to either print out and do the homework, or you need to do the homework on some kind of a device, tablet device, okay? If you're done and you feel comfortable and you know what you've done and you don't have any questions, you can go ahead and upload that into Canvas. That would be amazing. If you still have questions or you're still not quite sure about the uploading process into Canvas, bring it with you on Thursday. We'll start with questions, okay? You all should have a piece of paper now that has information from the board on there for me. There's this extra sort of desk sitting here in the middle of the the room right up here. If you guys will just put that on that table when you head out, I would really appreciate that. If you have any questions or you need to come see me, you know how to book You Can Book Me Now, talk to you about that. Or you can chat with me after class because we're done a little bit early. Other than that, I will see you guys all on Thursday. Have a lovely week.